Thank you very much for the introduction. So I want to start my talk by first briefly explaining the overall goal of our work. So when we define security protocols, we use a lot of different cryptographic primitives to accomplish certain goals. For example, we use symmetric encryption, we use MACs, digital signatures, Diffie-Hellman key exchanges, and key derivation, just to name a few of them. Then when we analyze the protocol, we have to reduce its security to the security of all of the primitives. Once we have done this for a single protocol, and we want to analyze a different protocol, then of course we have to redo all of the reductions again. And if we want to build a different protocol, again we have to redo all of the reductions, even if we use the exact same primitives that we used for the previous protocols, and so on and so forth. So we were wondering, is there any way to get rid of these reductions? And the way we want to accomplish this is to use modular proofs. That is, our idea is, why can't we separate the reductions from the actual protocol definitions, do the reductions just once, and then analyze arbitrarily many protocols based on these results. And modular proofs are provided by universal composability models, which is what we used for our approach. So I want to briefly explain what universal composability models are, and then explain our approach in more detail. In such models, we use simulatability to define security. That is, we are always talking about two different protocols. One of them is the real protocol, which we want to analyze and finally prove secure. The other protocol is called the ideal protocol or ideal functionality. This is essentially a perfect specification of some task. In other words, this ideal protocol is secure by definition. There is no way to attack it. Now, we say that the real protocol realizes the ideal protocol, or the real protocol is secure, if for all possible adversaries attacking the real protocol on the network, we can find an ideal adversary attacking the ideal protocol on the network, such that no environment can distinguish both cases. Or to put it a bit more informally, it does not matter whether we attack the real protocol. We could attack the ideal protocol as well to obtain the same information. However, because the ideal protocol is secure by definition, the real protocol cannot be any worse. There are several universal composability models in the literature, for example, the UC, IRTM, and the GNUC model. In our work, we used the IRTM model, which seemed to be the most suitable one due to its flexibility. So let me explain in more detail how we want to get rid of reduction proofs. Our approach essentially consists of 3 steps. In the first step, we provide an ideal functionality called fcrypto, which contains ideal specifications of several cryptographic primitives. We also provide another library which contains all of the implementations of these primitives, and then we show that pcrypto realizes fcrypto. This is exactly the step where we have to execute all reductions based on standard assumptions. However, this is a once and for all effort. Once we have done this, we can use it to analyze protocols. So say, for example, we want to analyze some protocol Q. Now we can use the ideal crypto library fcrypto as a subroutine to model the cryptographic primitives in this protocol. In a security proof, we then have to show that it realizes some ideal functionality f prime. So say, for example, Q is a key exchange protocol, so it should realize the ideal key exchange functionality. Importantly, in this proof, we only have to use intuitive information theoretic arguments. There are no reductions involved anymore, and usually we don't even need any probabilistic reasoning, at least as far as the primitives supported by fcrypto are concerned. Once we have done this, the third step is essentially for free. Namely, we can apply the composition theorem from the IRTM model to combine both security results and conclude that even if we base Q on the actual implementations of the cryptographic primitives, the resulting protocol is still secure. Now, if we want to analyze a different protocol, say a protocol R, then we only have to redo the second step, which, as I said, doesn't contain any reductions, and the third step, again, is for free, while the first step doesn't change at all. This is in contrast to a game-based security analysis, where we would have to redo all of the reductions for the new protocol. Let's take a closer look at the first step. So originally, the ideal crypto functionality was proposed by Küsters and Tüngertal, and it already supported several cryptographic primitives, including encryption schemes, signatures, MACs, key derivation, and nonces. All of them could also be used with each other. So for example, I could encrypt a MAC key, send it to someone else, so that that one could verify a MAC, for example. However, there was one major shortcoming of fcrypto, namely it didn't support Diffie-Hellman key exchanges, which are an important building block for many modern cryptographic protocols. So what we did in our work was that we added support for idealized Diffie-Hellman key exchange based on the decisional Diffie-Hellman assumption. Of course, we also provided a realization for this new library and finally proved that pcrypto indeed realizes fcrypto based on standard assumptions and for well-behaved environments. So providing this first step was one of the major contributions of our work. In the following, I want to give you an intuition of how fcrypto can be used in the second step by giving you some examples of which kind of API calls might occur during a protocol execution and how fcrypto handles these. So suppose we have two honest users, Alice and Bob. They want to execute a protocol together, and they use fcrypto to get access to cryptographic primitives. Now, during the protocol, Alice might decide that she wants to exchange a key with Bob via the Diffie-Hellman key exchange, so she asks fcrypto to generate a new Diffie-Hellman key share. Fcrypto responds by providing the public part, G to the A, and a pointer to the secret exponent A, which can then be used to perform various operations. Here it's important to note that Alice really receives the actual bit string G to the A, which she can use to perform computations or to embed it in the message to Bob. It's not like a symbolic analysis where this would just be some abstract term which you cannot really use to do much else. Also, fcrypto provides some security guarantees for these values. On the one hand, it guarantees that no key has already been created from this. On the other hand, it also guarantees that this exponent now is unique to Alice. Only Alice ever gets access to this exponent. It is not possible that any other user, by accident or even on purpose, generates the same exponent. Bob, on his side, can do the same, also ask for a Diffie-Hellman share, and he gets G to the B, which he can then send as part of a protocol to Alice. Once Alice has received G to the B, she can combine it with her own secret exponent, just as we would expect. And fcrypto generates a new key G to the C, which is sent to Alice. Note that I didn't write G to the AB, but G to the C, because this key is really independent of the exponents that were used to create it. Instead, fcrypto provides abstract security guarantees. In this case, it is guaranteed that only the honest users Alice and Bob can ever get access to this key and use it to perform whatever operation. Now that we have this key, we can, for example, derive other keys from it. Say at some point in the protocol, Alice figures, I need to send some secret to Bob, so I need a symmetric encryption key. She asks fcrypto for this key and obtains a pointer to a new encryption key. In this case, our security guarantee is that no one besides those that already know G to the C can derive the same key. Bob on his side, once he has received Alice's share G to the A, can execute the same steps, and at the end, he will also have a pointer to the same key in fcrypto. This key can then be used to encrypt messages, so say Alice wants to send some message M. She will obtain a ciphertext by fcrypto. However, instead of directly encrypting the message, fcrypto chooses a random bit string of the same length and encrypts that one. This way, we have the guarantee that even a computationally unbounded adversary tried to attack the ciphertext, the only information that he can receive from the ciphertext by definition is the length of the original message. So once Bob receives this ciphertext, he can decrypt it and will obtain the original message as we would expect. Note that this is just one example of some of the operations. There are many more. We could have also derived a MAC key. We could have encrypted that MAC key and sent it to Bob. We could have used digital signatures to provide some kind of authentication. Now, I've only talked about honest users using fcrypto, so what about dishonest users or users owning corrupted keys? Fcrypto also models this setting, and it does so by separating the keys into two sets. One of them are the keys owned by honest users. These are the keys where we have security guarantees, and the other keys are those that are corrupted and potentially known to the adversary. In this case, fcrypto cannot provide any guarantees at all. So say, for example, someone wants to encrypt a message with a corrupted key. In this case, fcrypto just directly outputs the actual encryption just as the implementation pcrypto would do. Again, this is just an example. The same holds also for all of the other primitives supported by fcrypto. This concludes our brief look at the API of fcrypto. In our work, we also took a look at a specific class of protocols that is often analyzed in the second step. Namely, we looked at key exchange protocols and the ideal key exchange functionality. So traditional formulations of the key exchange functionality work roughly as follows. We have this functionality which can be accessed by some users to perform a key exchange, and at the end, the key exchange functionality just directly outputs the key in the form of some bit string to the users. They can then use this bit string as a key for some cryptographic primitive in a protocol execution. However, this means that if we analyze this protocol, again, we would have to do reduction proofs, which is exactly what we wanted to prevent in our approach. It would be much nicer if we also could have used this key ideally, similar to what was possible with fcrypto. So what we did in our work is provide a new definition of an ideal key exchange functionality. This functionality has a copy of fcrypto built in, and instead of outputting a key, both users get access to the same key within fcrypto that can then be used ideally to execute a protocol. Now, if we prove the protocol to be secure, so for example, say we wanted to build a secure channel based on the key exchange, then again, we only need information theoretic arguments for all the primitives that are keyed with this key. We don't have to do any reductions anymore. Once we have done this, we can apply the composition theorem to first replace the key exchange functionality with its implementation, and we can iterate this to also replace the fcrypto library with its implementation, yielding a real protocol which is still secure. We illustrated the usefulness of our approach by analyzing several Diffie-Hellman key exchange protocols from the literature. Namely, we looked at one of the protocols of the ISO 9798 family. We analyzed one version of a Sigma protocol, and we looked at the non-static mode of OP-TLS. In all of these cases, this was the first faithful analysis in a universal composability model. In case of OP-TLS, we tried to prove security. However, the proof didn't go through. So we looked at the original game-based security proof, and we found a flaw. Namely, the original game-based proof used the decisional Diffie-Hellman assumption. However, we noticed that this assumption is indeed not sufficient to prove security of this protocol. So what we did, since fcrypto is based on the decisional Diffie-Hellman assumption, we analyzed a slight variant of the protocol and then showed for this variation that it is indeed sufficient to assume to use the decisional Diffie-Hellman assumption to show the security. To conclude my talk, we did indeed succeed in our goal of eliminating reduction proofs, at least as far as the primitives supported by fcrypto go. Our approach is highly modular. This was also already illustrated by, for example, the ideal key exchange functionality, which can be reused to build higher level protocols on top of it. And then we can combine security results via the composition theorem. And we have very strong universally composable security guarantees. That is, we know that our protocols stay secure no matter in which context they run, because we analyze them for arbitrary environments that try to attack them. In our paper, we also discussed the differences between our approach and other approaches, such as game-based security analysis, symbolic analysis, or implementation-based analysis, such as the one we already saw yesterday in the TLS session. In future work, we want to implement further Diffie-Hellman assumptions. Why this is, again, quite some work. And this is once and for all effort. As I've shown you, we have to do this a single time, and then we can use it to analyze arbitrarily many protocols based on it. It would also be interesting to look at, to see whether current tools for automating proofs can benefit from our approach. And of course, we want to apply it to analyze further protocols. Thank you very much for your attention.
Do we have questions? Bruno?
So nice talk, many interesting results. I have a question about the compromise. So do you consider dynamic compromise or just static compromise?
So it depends a bit on the primitive. In case of signatures or MACs, we consider full dynamic corruption. In case of encryption, because we replace the encryption with these random bit strings, we have to tone this a bit more down. So instead of full dynamic corruption, we say that a key may be corrupted at any time before it is used for the first time. Once it has been used, the corruption is essentially static, so the adversary has decided on whether this key should be corrupted or not.
Okay, and do you consider the compromise of ephemerals in the Diffie-Hellman exchange?
Excuse me?
Do you consider the compromise of ephemerals in the Diffie-Hellman exchange?
Yeah, we also consider corruption of the Diffie-Hellman exponents, but there we have a similar problem once they have been used to create an ideal key, because we replace this key G to the A with G to the C. Once it has been used to create a key, the corruption status cannot change anymore.
Thank you.
Any other questions? So I have one regarding forward secrecy. So can you tell us how forward secrecy manifests itself in your setting? Is it something that you prove additionally or something that is implicit?
Excuse me? I didn't
what do you see about, how do you get forward secrecy properties? So using a Diffie-Hellman key exchange, do you get, as compared to what you could do previously with F-crypto, you get forward secrecy, and I'm wondering how it appears in the model.
Well, so essentially the idea of forward secrecy is that someone cannot get access to what is done in F-crypto once the users have forgotten the keys. There's no way to access the information, for example, what has been encrypted with some key in F-crypto, because the box is closed. And once the user says, okay, now I will forget my session key because I don't need it anymore, there's also no way for an adversary to later on get back to the contents, because F-crypto doesn't allow the adversary to get access to this information.
Okay. But so is it an implicit property of the ideal functionality, or do you have a way to erase secrets, for example?
Well, it essentially depends on the modeling of the protocols that we analyze. So the protocols, the case studies that we analyze, we could say, okay, at the end of the session, when the key is used, we will simply forget the key, which we modeled by forgetting the pointer, the access to this key in F-crypto. And then we could argue, because there's no way to access this information anymore, there cannot be any way for an adversary to decrypt any messages, for example, encrypted with the session key later on, because he cannot get access. So it's not inherent to the UC model itself, but it depends on the modeling and uses this, this feature of fcrypto that no one can get access to anything if he doesn't have a pointer to one of the keys.
Okay, thanks. So let's thank the speaker again.